Hello everyone, it's September 11th. Alright, we skipped yesterday because I was too tired and it's a hard problem anyway, so I'll just try it today and we'll see how it is. I mean, the previous one was that stock sale and exchange, that thing. I mean, that thing was a little bit disappointing because I've done that many times, but eventually still need to check back on the previous solution to kind of understand how the state machine works. I get a full understanding now. I think I understand now, right? I know how it goes, but I think eventually if it comes back again, I'm probably still gonna have trouble with that. But anyway, that's beside the point. So this is what we have today: a maximum performance of a team. Apparently, I've done this before. All right, let's see. Two integers, n and k, speed and efficiency. Okay. Two integer arrays. N engineers, number from 1 to n, speed I and efficiency I represents the speed and efficiency of the ith engineer respectively. Choose at most k different engineers out of the n engineer to form a team with the maximum performance, which is the sum of the engineer's speed multiplied by the minimum efficiency among the engineers. The sum of the speed multiplied by the minimum efficiency among their engineers to the maximum performance of the team. Engineering 201. I won't call engineer 2. Number from 1 to n. What? What are you talking about? So unit 2 is actually this one, right? 2 with efficiency 4. Engineering 5, it's a 4, 0, 1, 2, 3, 4. It's a speed is 5, efficiency is 7. 10 plus 5, so speed times 5. No, times 4. Basically, we want a subarray, right? A subarray multiplied by the minimum of the corresponding. If you go 3, well, I do have 3 examples to work with. 10 to the 5th. Oof. And most k. N is actually not necessary. N is the equals length of the speed and efficiency, right? Yeah, n is actually not necessary. K is necessary. So we know we only pick 2. We only pick certain number, right? And the best we want to do is to get the maximum on the speed and multiplied by the best efficiency. That's what we want to do. So maybe we should sort if speed. Okay, we can sort speed. Will be 10, 8, 5. 10, 8, 5, 3, 2, 1. So correspondingly, that can be 5 and efficiency. Not 5, 4. 2, 7, 3, 5, 9. Right? That was the efficiency. So we have these two. So what we want is, we can check the largest value on the efficiency, which is 9, and we see how many do we have. And we don't have enough, so we'll include the maximum, and then we add another one, and then we try to see how big it is. We say, oh, okay, it's not gonna work. So next we'll try 7, right? We try 7. And 7 points to 5, and then we try the 10. Oh wait, hold on. We do the minimum. Multiply by the minimum efficiency. So the maximum efficiency doesn't really matter too much. We just want a minimum to be big enough. Minimum. I'm thinking about a monotonic array. A monotonic increasing, because we already sort the speed. So the speed is going to big to small, right? We reverse sort it is a big to small. So ideally, we want to include the biggest one, which means we want to include the biggest, the efficiency of the biggest value. So if we're going on and efficiency is smaller than the biggest value, then we discard it. How do you make this decision, right? How do you make this decision? You discard it. It's determined by the minimum performance, minimum efficiency, right? So maybe we should sort by efficiency. And if we sort by efficiency, then we can say, okay, the best we can do is to take, if k equals 2, the best we can do is take the 2 highest. No, is to have, because you cannot have the highest efficiency if you have more than 2 people, right? If you have 2 people, then the highest efficiency you can get is always going to be the second best efficiency. So it could be like, what is the maximum we can get at an efficiency? Let's sort based on efficiency and see what happens. So it'll be 2, 3, 4, 5, 7, 9. All right. Correspondingly, it's going to be 8, 3, 10, 2, 5, 1. All right, that's correspondingly what we have. So I have 2 people. So if I take efficiency 2 as the smallest, then we can pick whatever else we want, which means we can pick the largest, right? We can pick the largest time. So in this case, if I pick 8, then we can pick 10 as the largest. So it's 10 plus 8 times 2, so we get 36, right? Then we can pick 3, then that's 3. Then we can pick, again, 10. So it's 13 times 3. That's 39. If we pick 4, then we already have 10. Then the second largest is going to be, it cannot be 8, right? Because 8 is to the left. So it has to pick something on the right, right? We need to pick something on the right. I'm going to pick something on the right. The largest is going to be 5. So it's 15 times 4. That's 60. If we do 5, then we have 2. When we pick something on the right, that's 5. So that's 7. That'd be 35. We pick this, something on the right, that's only 1. That's 42. And the last one is just 9. Oh, we cannot do the last one because we don't have 2 people. Okay, so we sort based on efficiency. And we pick the smallest efficiency, right? And then we pick the largest on the right. How can we do that more efficiently? The largest on the right. Well, this is the largest in, can we binary search this? How do we binary search this? I mean, it's segment tree, right? It is essentially segment tree. We sort the efficiency, and then we have the speed. Then we build a segment tree out of the speed. Then, but actually it's not just the largest. No, it's not just the largest. We want the sum of the largest on the right side. And we need to do it fast. What do we do? Yeah, and imagine you have 3, then we have the largest 2 on the right side. We're going to pick 2 out. Well, we can get to it, but just how do I find the largest k values in an array? All right, that is essentially the problem, the largest k values in an array. I mean, we can sort, but we have the issue. Well, let's sort, and then we have their positions, right? Let me just try and see if it's variable. Okay, so these are the positions. So now we know the position, then we sort this thing, okay, from big to small. So we have 10, 2, 8, 0, 10, 8, 5, 3, 2, and 1, right? So this is sorted speed attached with the order in efficiency. So if I take the first one, right? The first one is 8, 0. The position is 0. So I need to find the largest one on the right side with the value bigger than 0. And what I found is I have 10. All right. That is the largest that I can use. I mean, a heap? Are we saying a heap? Three can use 10. 10 comes in, so we need to pop. So it's 5. But we have to search every single time. Right, so it's O(n) log n to sort, and then O(n) k. We'll have to go through every single time and do multiplied, yeah, because we go through the k times, so O(n) k. Do you think it's gonna work? What's k? K can be 10 to the 5th. I was talking about 10 to the 5th to 10 to the 5th. That is not gonna work.
It's new, right?
This is new. We have Prime Video and Prime Music. Yeah? Yeah, it will work if it's only k equals 2. But it won't work. It only works if k equals to 2. Why would you say that? Because I can just take the top, right? So every time it's the top, every time it's the top. And then if the top has been counted before, I just pop. Yeah, so if it's k equals 2, I can solve this. But if k is larger than 2, k is larger than 2, I can't just go through everything. That ain't gonna work. Okay, what do we want? All right. What we want is hold on. What we want is the sum. All right, we don't really care. I want the sum of the largest values on the right side, and with numbers, with the ones that's already been visited. ignored. That's what we want. And the values can repeat. I don't think this is unique. So what I'm saying is, if we can do a prefix sum on the right, okay, a prefix sum on the right, then we pick a value on the left, and then what we want is on the right side, we need to search for the prefix sum, right, of the top. Hold on, what's the idea? We can binary search to locate where that thing is. Okay, we binary search where that thing is, and then we binary search, so we know, let's say 8 is at this position, and we want to know, right, and we want to know if there are enough to the left, because that's bigger, right? If there's anything to the left that can fit the one we want. Like if I have one of this, so I need F1, I need K minus 1 on the right side. So I binary search to locate where this value is, right? I'm looking at 8. So I binary search on the right, try to see where 8 is, and I found it. And then I see on the left side, if there's enough on the left side, I just pick the top. Then boom, that's the maximum solution we can have. Now we'll go on to the next one. Binary search 3, we got it. Okay, and then we need a binary search on the right, like this. And then we again do the top, but we need to minus the 1 if it's included. Oh, minus the 1 that's included. Lordy. How are you gonna do that? How are you gonna do that? I mean, I can keep track of their positions. Okay? So, given a value, I binary search it so I know where it is. So I know the range of all the things larger than me, like how much they cost. I know that. And we'll see. Oh, and we have a situation. If it's not enough, then we have to go on the part that's smaller than me. Yikes. Alright, no idea. Let's see. I put out good interview questions. I don't know, let's see. Greedy. Looks greedy to me, right? Yeah, because this is an ON. It seems greedy to me. Or ON log n. The hint is greedy. I have no idea. Let's see. Better efficiency in decreasing order. I have that in increasing order. Okay. Then what? Let's hit number 2. Starting from one engineer to build a team. It suffices to bring k-1 more engineers who have higher efficiencies as well as high speeds. So we are targeting the lowest engineer, lowest efficient engineer. So that's our bottom line, right? Then we need to find k-1 who have higher efficiency. So to the right, that is true, and also has as high. Yeah, that's the same idea I have. I secure the lowest efficiency, now I find the maximum speed on the right. But the problem, how do I achieve that? They say to use a heap. But how do I use a heap to achieve that? The thing is going to still cost time. I can secure the lowest, that's fine. And on the right side, I have an array. I need to find the top, the maximum k-1 value in an array. So how do I solve this problem? Maximum k value in an array. That's the problem I need to solve. I don't know how. K largest element. Let's see. Yeah, this is where I got stuck because otherwise the problem is solved. That doesn't seem to be a difficult problem, but use bubble k times. O(n) times k. Selection sort. Selection sort. Ah, selection sort. Sort the first k elements. Find the smallest element in temp. Let the smallest element be min. For each element in the remaining, if k greater than the minimum, then remove and insert k. Look at that. I think I got some inspiration out of this. Which means we will build a heap, right? A min heap. But we don't want to do this every single time. Because on the minimums are top, okay? And then we'll do these two. Right, and then as we go, if something's bigger than, we pop this and we add this. We pop the top or we add. We pop the top or we add. And eventually, once we're done, So it will be O(n) log n. Wait, hold on. No, that's O(n) log k. It will be O(n) log k. Or we can sort. Monotonic array. That's O(n) squared. Ain't gonna work. Well, you have to go through O(n) anyway. Let's say we get a k largest. We can sort and get a k largest. Put that in a heap. Okay? And then we start from the first one. No, we start from the first one. Now we get a k largest here. Okay, so first one will be done. Next we move on to this, and then we say if this is, then we need to pop this. Then who do we add? Still, implementation is unsure. What's the implementation? Yeah, I don't know the implementation. Alright, let's see what's the implementation. I got the idea, but no implementation. We know the sorting, and we have a heap. Speed sum. hold on, let me see again. So I know to sort the efficiency, right? And then I have a speed sum, which is the maximum sum of everyone. Okay, let's think about it again. If we go from right to left, right? For pick any efficiency, we need to find the maximum sum on the right. Maximum sum on the right. And let's say we have the maximum already there, okay? Let's say we have two values on the right. And then, okay, so if we've got two values, then this is the first one we get. So we have to use these two. There's no other way, right? We have to use these two. Then I'll have the smallest value. Then we move on. Then we can maintain the largest two values. Because we walk from right to left. If we walk from right to left, then every time, then let's say we have the k largest value on the right, we already secured. And every time a new value comes in, we compare to the smaller of the k. And if it's bigger, then we will kick one out, push one in, right? Kick this out, push one in. Oh, I see the solution. How do I count this one? I mean, I did see the solution, but I got the majority figured out by myself. I count it as improvement, but still need a little bit more work. Yeah, I figured. So, yeah, that's not too bad, right? Still struggled, but I was able to figure out the general process. I knew that if we fix the lowest efficient engineer, all we need to do is to find the k minus 1 engineer with the largest speed that have higher efficiency than the lowest efficient one. Now the problem is to find the k plus 1 max speed in any given array. And I was stuck at this step. Now the solution, which I checked from my previous attempt, is that we go from high efficiency to low. Alright, thus we will get we run a heap of size k minus 1, which keeps the highest k minus 1 speed seen so far. Each time a new engineer is encountered, we compare that to the top of the heap, main heap. if the new engineer has larger, right? Has larger speed than the smallest speed in the heap, we swap them. We also keep track of the sum of the top k-1 speed. This way, each swap incurs O1 time to recompute sum. Make perfect sense. So we just need to sort. All right. Yeah. What we call this? Combined equals sorted. The efficiency and the speed for E as in zip. Speed, efficiency, reverse equals true, right? So we have efficiency is speed. Efficiency goes first, speed goes second. And we want it doesn't really matter. It doesn't really matter because we use heap. Okay. Then we say largest k-1. I'll just call it heap. Heap will equal to the last k-1 value. I just do this, right? And then combine sum is 0. Then we go from the right to left. Well, actually, because we reverse sorted, so going from front to back. So we say for efficiency and speed in combined. Okay. If len heap is smaller than k, -1, and heap q dot heap push heap speed, right? Else it's equal to. Okay, so we are countering this. Oh, hold on. Combine sum plus equal to speed. All right. Else, if the heap is equal to, so heap added, go to the next one. Heap is not, we add it. Go to the next one. Heap is equal to k-1. Okay. Then we need a result. It's equal to this, and then, which means this, and this is k-1, and that's guaranteed to be the biggest, right? Then we just do res equals maximum the res, combine sum times efficiency. The current efficiency is the smallest efficiency. Once we've done that, we need to say if heap 0, main heap, is smaller than current speed, then heap q dot heap push heap. No, we first heap q dot heap pop. We need the pop, and then we push current speed in, and combine sum will plus equal to it's a temp. We pop it, push it, and be temp, minus temp, right? Minus temp, so S minus temp. Then we go back. Yeah, this is just to maintain, right? Maintain the top k minus 1 speed in heap. And when we're done, return rest. Let's see. We didn't use n at all. Two. Okay. N speed efficiency. Okay. Oh. Generator. What? 32. What? That's pretty stupid. I multiplied. Huh? Let's see. ES heap. So we have 10 for oh my god, that's S and E. Should be efficiency first. Oh, why don't you just zip it? Yeah. Alright, so it goes 9-1, right? Nothing. And then we go 7-5. Let's do it at the end. Seven five will be combined sum of 1. I forgot to add the current one. Speed. Yep, I forgot to add a speed. Oh. Let's see what's wrong. Expect 56. Let's go ES combine sum heap. So we have 7, 8. If we sort by efficiency, right? So it shall be 7 to 1, which corresponding to, this is the efficiency. Speed is going to be 8 to 2, right? Yes, 8 to 2. So efficiency, and then we have k equals what? K equals 2. So the first one doesn't work, so the second one. So efficiency is 2. The hell? Efficiency is 7. Right? So now efficiency is 2. So 2 times... Oh! At most. Screw you. At most. Because we start from the biggest efficiency, right? And as we go on, we add in more. If we add in more, oh, I see. So we have to handle these one as well. I see. So we shouldn't skip this one. So this is the first one. Combine sum plus this s times this. Yes, that is true. And then we say temp equals heap q dot heap pop heap if len heap is equal to k minus 1 and heap 0 is smaller than s. Else zero, which means if the heap size is small, we don't have temp. If the heap top is larger than or equal to s, we don't have, and we also don't pop. Then when you say heap q, yes, then we push it in. Okay. And other than push it in, we can also do this. Right, we can push s in because we popped, or we don't pop, doesn't matter. And then we increment this. There we go. That's the one. Ooh, the first one is wrong. Shoot. I thought we got it. 1, 2, 3. What the hell? K minus 1. Smaller equal to. It was smaller equal to. Oh, hold on. It should be right. Why would it become bigger? Alright, we currently have 1. Now I got 5 because it's bigger, so I swap it. And now it's equal to this, yes. But this is false. I should not push. Need to handle it better. You can say temp equals 0. Okay? And then if this, then this, and this. Huh? No. As if it's smaller, then we do it. If heap and then we always pop. And then if len heap is smaller than k-1, we always push. That's still not right. Combine sum as the previous, right? The largest. We always plus s times e. That's good. Then let's see if this needs to get popped. Now we say if this is smaller, then we always do that. Maybe we should do it this way. If it's smaller, if it's equal to, and this. If it's smaller, we always do this. And hold on. Else if this temp equals this, and we need to push again. No? What? It was working earlier. If heap length is smaller than k-1, yeah, then we just push, and then combine sum, just add. It's perfect. If it's equal to, k minus 1. Then we check. Okay, we check. But it does not look right because we have 10. So we go from 1, right? Now we go to 7, 5. What's this? Combined sum. Is 5. So the star land heaps nothing. So we will push speed into it. And combined sum will be 1. Yes. Next round. Combined sum plus s. Yes. Times this is right. And this is equal to. So we check. It's smaller than current. Yes. So we swap. Right, so we pop the heap, and then we push the new, and then for the combined sum, we need to add the current minus the temp. That's also correct. So combined sum becomes 5, right? Combined sum becomes 5. So we only have 1. Next, we'll go to 5. That is 2, so we don't disturb. I should print this one as well. First is 9, second one's 42. Yeah. Next one 35. Next one 68. This one has issues. 35 is alright. 68. 10 and 4. How would you calculate 68? What's 60 divided by 4? 17. Where did 17 come from? 10 plus 7. How is it possible we have a 7 combined sum? How? Combined sum is 5. So we'll have 1 combined sum and then 5 combined sum. And that becomes 7. What? 5, 2, 7. That's bonkers. Oh, we should not plus s. Then why do we do this? The whole point, right? The whole point is trying to. Oh my god, this one I have to add as well. The whole point is trying to combine, because you see this one and this one, they're repeating. So that's why I want to do a temp, right? If I do a temp here, and then we can say plus equal this minus temp. which means I can do both here because these are the same. So I don't need to do this. All I need to say is if this is equal to and heap 0 is smaller than s, then we do this. Man, it's not working. How? Okay, hold on. So this one works, right? This one works. So if this is smaller than this, we do it. If it's equal to and is smaller, then we do this. But if this is larger than, we don't do it. How do I combine these? What's the else? The else is not, just don't do anything. Screw this. Let me just do it this way then. Seriously, screw this. I just do it this way. It's not worth it. So, and I can combine these two. I don't need this. This has to happen earlier. Like this. Alright. We do this. If this, we do this. If this, we do this. And we also have to push the S. Yeah. There we go. At most k, thus we have to keep track when the number of engineers is smaller than k. That's it. Come on. Runtime error. Oh, we have to handle this one as well. If this is equal to no, Oh. Damn, man. So heap. Let's try this one first. Yeah. Oh my god. Dude. Like, what the hell? I forgot to modulate. That is a stupid mistake. Modulo. Alright. I wonder if it's gonna be... Oh, first of all, we hit 800 days.
Congratulations.
Thank you very much. I wonder if we can... No, we have this multiply. Nah, I don't want to change. I just do it this way. It's alright. That's alright. Where's O and log K? Do we have more test cases than before? Oh. I have efficiency and speed. We always pop the smallest and always push current. Why would I do that? I just feel like this is not gonna work. I'm always sacrificing the current. What if the current smallest is larger than the S? I don't know. Yeah, this doesn't feel right. I understand I push a small, but what if the smallest is really big and the big one is smaller? I could have used those instead of... So, for example, what I'm thinking is, let's say that's the efficiency and the speed. Like that. And I will say before. because greedy. Because when I pop this, this has already been used, right? So if S is indeed larger than this, if S is larger than, then yes, we shall always push it in. If S is smaller, right? If S is smaller, then we have already done it. The speed, the previous ones has already, the bigger version has already gone through, and now we have something smaller, which is perfectly fine. We have something smaller, even if we don't swap. Even if we don't swap, it's going to be the same, right? If I don't swap, because the bigger versions already have its result. So I swap or don't swap, it doesn't really matter. It doesn't matter. Because if I don't swap, then the current one will have a bigger value. Agreed. It will have a bigger value, but that will not be as big as the previous one. So it's an interesting twist. So this is an interesting twist. Don't have to check heap 0 smaller than S, because if heap 0, we don't have to check, we can directly pop heap and push S. We can do this. This is because if heap 0 is indeed smaller than S, it works. Otherwise, we know that heap 0 has already been involved in the previous computation, right? It has been involved in the previous computation with an efficiency not smaller than the current efficiency. This means we have already generated a result that is bigger, that is not smaller than the current. We have already generated a result with the previous efficiency that is not smaller than the result generated from the current efficiency, even if we do not swap out heap 0. Hence, although we won't get the biggest result at each efficiency if we swap heap 0 every single time, it is guaranteed that the largest result will have always been encountered. So the change is we do this, and if we do this, then we just simply don't do this. Yeah, we just simply say if Oh yeah, this is actually more complicated. You know what? I'll change it. If len heap is equal to we can say if heap and this one is equal to this, then we always do this. Alright, and then we simply push this. If not heap, or if this is smaller, right? How does work? Nope. I'll just do if len heap is equal to k. Too big. Then we do a combine sum, right? And then res equals max res combine sum times current efficiency. And this one add. Nope. Shouldn't we push it first, right? Nope. There we go. We always add it first. Add this. I will always add it. And I will always pop. go faster. Right. We save some of the if and else. Okay, that'll be it. Let's check on the number of test cases. Oh wow. Previously 54. Now it's 55. They added one test case. Alright, that'll be it. I'll see you guys tonight. Adios.